We are looking at the topic of discrete probability distribution, and the first part of that is probability distribution. So we will cover probability distributions in general. We move on to binomial probability distributions, and then briefly explain Poisson probability distribution. The objectives: we're going to construct a probability distribution for a random variable. We find the mean, variance, and standard deviation. Also expected value, which is in essence the same as the mean. We find the exact probability for X successes in n trials of B, D, or binomial experiment. And we're going to find the mean, variance, and standard deviation for that. In the previous chapter, we covered basic concept of probability. So let's quickly recap what we have done. Probability is always between 0 and 1. The sum must always be equal to 1 or 100%. When the probability is not going to happen, the probability is 0, we say it's an impossible set. If it's 100%, we call it a sure or certain set, in which case, again, the probability is 1 or 100%. Two events are complementary events. If they have nothing in common, they are disjoint, and their probabilities add up to 1. The actual odds against an event A is defined as the probability of A complement over the probability of A, and the actual odds in favor of that event would be the reciprocal of that. Normally we use integers like A to B to represent both cases. And it gives rise to the definition of a pair of odds, and therefore the net profit becomes the product of the pair of odds against an event A times the amount of bet. The addition rule in probability of A union B is equal to probability of A plus probability of B minus the probability of A intersection B, because probability of A intersection B is accounted for twice, once for A, once for B. Multiplication rule: if the events are independent, we simply multiply probability of A times probability of B. If not, then it becomes the probability of one times the probability of the other, given the first one has happened, using the conditional probability. In other words, probability of A given B is defined as probability of A intersection B over the probability of B, and probability of B given A is given as the probability of A intersection B over probability of A. Complementary events, again, is explained here. Their probabilities add up to 1. We also have this notion of the probability of at least 1, which is easier to calculate the probability of none and subtract it from 1. So probability of at least 1 is defined as 1 minus the probability of none. Conditional probabilities are defined here. Again, at the bottom, I mentioned that. And the idea of events being dependent or independent. They are dependent when probability of A given B is not equal to probability of A, and they are independent when the probability of A given B becomes probability of A. In other words, conditional probability become marginal probability. We also looked at the counting rules and how we use a calculator for that. We have the fundamental counting rule. If one can happen in m different ways, another one in n different ways, you simply multiply. Factorial was defined n factorial, which starts from n, and you multiply by every number smaller than that by 1 all the way to number 1. 0 factorial and 1 factorial, they both end up being 1. Permutation and combination were discussed. In the case of the permutation, order is important. The case of the combination is not, and that's why for permutation the formula becomes n factorial over n minus r factorial, whereas in the case of the combination we divide the same thing by r factorial. In other words, combination becomes n factorial over n minus r factorial times r factorial. This is in case we have different items But if the items repeat, then we use the permutation rule known as distinguishable permutation, where the calculation becomes n factorial over n1 factorial times n2 factorial times n sub k factorial, so on and so forth. So that is the synopsis of what has been covered. Probability distribution, basically what we have done, we have looked at describing data, we have looked at probability, and now we're going to combine these two with what we call a probability distribution. So combining descriptive methods and probabilities, construct probability distributions by presenting possible outcomes along with their relative frequencies. In essence, in the case of a discrete random variable, I hope everybody remembers when we looked at quantitative data, we said there are two types, discrete and continuous. And discrete is countable. So in the case of a discrete, we have basically two columns, the outcomes, what X represents, and then the probability for each case. Those two sitting next to each other, they define for us what is called probability distribution for a discrete random variable. For a continuous random variable, there are infinitely many numbers in between, and it becomes a continuous function and a continuous graph. Key concepts: probability histogram is a graph that visually depicts a probability distribution. We want to find its important parameters, which are mean, standard deviation, and variance. We want to determine whether outcomes are significant, that means significantly low or significantly high.
A random variable is a variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure.
Next paragraph, probability distribution.
Probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, formula, or graph. A discrete probability distribution consists of the values a random variable can assume and the corresponding probabilities of the values.
The next one, discrete random variable, and remember we're going to use DRV for short.
A discrete random variable has a collection of values that is finite or countable. If there are infinitely many values, the number of values is countable. If it is possible to count them individually, such as the number of tosses of coin before getting heads.
And finally, continuous random variable. Sometimes we use CRV to represent that. CRV versus DRV.
A continuous random variable has infinitely many values, and the collection of values is not countable. That is, it is impossible to count the individual items because at least some of them are on a continuous scale, such as body temperatures.
So those are some definitions we need to know. So there are three requirements for a probability distribution to work. Number one,
there is a numerical, not categorical, random variable RVX, and its values are associated with corresponding probabilities.
And the next one?
The sum of the probabilities is equal to 1, where X assumes all possible values. The sum of all probabilities must be 1, but some such as 0.999 or 1.001 are acceptable because they result from rounding errors.
Finally, the last one.
The probability must be between 0 and 1 for every individual value of the random variable x. That is, each probability value must be between 0 and 1 inclusive.
So in short, what are the requirements? Got to deal with numbers. The sum is always 1 or 100%. Sometimes, due to round off error, we may have a very close number. That is understandable. Finally, probability can only be between 0 and 1. So that's the main thing we want to get out of this section for now. Probability distribution. In the first example, we are constructing a probability distribution for rolling a single die. Just remember, all you have to do for a DRV, discrete random variable, all you need is X and P of X. All you have to do, fill up those two columns. So X in this case represents the outcome, and P of X the probability of that specific outcome. Now, when we are dealing with rolling a basic die, there are 6 sides, and so X can be number 1, 2, all the way to number 6. Also, the probability for each case is equally likely. It's 1 out of 6. So this is basically what we mean by probability distribution. In this example, we are given the probability distribution. So if somebody says, what is the probability distribution for a sample space or for tossing 3 coins, this is given right here. Now understand, for 3 coins, depends on what X represents. By the way, whether it represents the number of heads or tails, it works out to be the same. I want you to know. But specifically, X represents the number of heads. And since there are 3 coins, then we have only 4 choices, 0 all the way to 3. Now, we have seen the tree diagram for this. We have seen the sample space for this. We have seen the probability for each case previously, so I don't think you have anything to worry about. To remember that the probabilities on the second column are as follows: 1 over 8, 3 over 8, 3 over 8, 1 over 8. And again, you could always do this. Remember, we did it for genders, so this works out the same way: H and T, H and T, H and T. So the first stage, the second stage, and the third coin, that means the third stage, or 2 cubed, or 8 outcomes. The third one goes something like this. For example, if you put H here, this means H, 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 and this last one means T, T, T. And you can fill up in between. So all we have to do in this case, we want to represent it with a graph or a number line. So all you have to do, just come up with a horizontal line and a vertical line. Horizontal line represents the X. And so the X could be 0, 1, 2, or 3. And the vertical axis is the frequency or percent frequency, which really becomes the probability here. Frequency, or in this case, percent frequency or probability. Needless to say, you realize the left column in both cases are numbers, and the right column, the probability, they add up to 1, and they're all between 0 and 1. Here's the next one. Tossing 2 coins, where X represents the number of heads, and we end up with the following given at the bottom as the probability distribution. So if somebody asks you what is the probability distribution for a specific case, if it's a discrete random variable, it simply means come up with the following table. Of course, if X, we have too many of them, then it may be difficult to set up the whole table. We may even give a formula, just as an example. So with that being the case, there are 2 coins, so we have maximum 2 possibilities for number of heads. And again, you can go with the tree diagram, look at what we have done before. Is this a probability distribution? Well, the first thing we need to look at is the first requirement. There were 3 requirements. In short, the X should represent a number. It should be numerical. Some must be adding up to 1, and none of them is beyond 1. That means larger than 1 or less than 0. The variable is a numerical random variable. So far it works, the first requirement. The second one, the sum must be 1. So we add up the second column, 0.25, 0.5, 0.25, and they must become 1. And as you can see, the second column, all the numbers are between 0 and 1. So therefore, the answer is yes, absolutely. So X is a discrete, and remember, discrete means numerical in essence. So even if you just said it's a discrete random variable, that's good enough. Discrete means it is a discrete numerical value. It's countable. So there are 3 possible values. 3 is a finite number, and it satisfies the requirements of being finite as explained in the 3 steps. So basically, when you do those 3 steps, 1, 2, and 3, that they have a check mark next to them, you're done. Probability distribution, a probability histogram.
A probability histogram is a graph of probability distributions that displays the possible values of a discrete random variable on a horizontal axis and the probabilities of those values on the vertical axis. A vertical bar represents the probability of each value, and its height is equal to the probability. And then this is a probability histogram for a number of heads when 2 coins are tossed.
when we did the histogram, the vertical axis could be frequency or percent frequency. In essence, we are really using percent frequency, which is now the probability. That's the idea behind this. So with that being the case, a probability distribution could also be in the form of a formula. For example, if this one is given, a p of x is 1 over 2 times 2 minus x factorial times x factorial. So that's the formula. And for x equals 0, 1, or 2, that means it works for those three numbers. You're going to replace the x with 0, come up with the answer. 1, come up with the answer. 2, come up with the answer. So the idea is sometimes we may have a formula. And normally when we have so many numbers, as we come across it later on in this, you can calculate each one. I'm assuming nobody has any problem calculating this. P of 0 is 0.25, P of 1 is 0.5, P of 2 is 0.25. And in this case, the reason we end up with 2 only because we are dealing with 2 heads max. And it's very easy to calculate. You can try this on your own to make sure you come up with the correct answer. A probability distribution can be represented with a table, as we did it in the previous page. We can represent it with a histogram, with a graph, or with a formula.
Hiring managers were asked to identify the biggest mistakes that job applicants make during an interview, and the table below is based on their responses. Does the table below describe a probability distribution?
So what do you think? Does it?
No.
No. Any idea why?
They're not numerical random values.
If you look at the very first one, is that x is supposed to be a number. It's not, you don't even have to check anymore. I want you to know that. But let's check everything. So the first one is out, so is this as a probability distribution. But here's how it works. Okay, the first requirement is not working. The second requirement is not working. The third one, each one is between 0 and 1 is working, but really 1 is good enough to say this is not describing a probability distribution. Let's look at some formulas. So when we deal with probability distribution, there are some parameters of a probability distribution.
Remember that with a probability distribution, we have a description of the population instead of a sample. The values of the mean, standard deviation, and variance are parameters, not statistics.
The mean, variance, and standard deviation of a discrete probability distribution can be found with the following formulas: mean, expected value, variance, and standard deviation of DRVX. Mean, the expected value of occurrence per repetition. It represents the average value of the outcome.
So let's look at the formulas. Mu or E of x, the expected value, is the summation of x p of x. In other words, if you recall the probability distribution table, you just multiply the two columns and it becomes the next column, you add them up. Variance is defined as sigma squared equals the summation of x squared p of x minus mu squared, and sigma is the square root of that. Now, what I want to quickly show you, I used to prove a lot of things, and I noticed not a lot of students were following. So I'm going to just give you the proof. You can go over that. A couple of things that I want to mention is that how we go from here to here, how we go, for example, from here underneath to here. You can expand x minus mu squared. So x minus mu squared becomes x squared minus 2 mu x plus mu squared. That p of x, which is being multiplied by it, remains. So you distribute that and you get x squared times p of x minus 2 mu times p of x, 2 mu x times p of x plus mu squared times p of x. And so if you write them as such, this is the same as mu, and this is the summation of p of x must add up to 1. That's how you get to the proof if anybody is interested. Let's look at an example. By the way, remember p of x in essence is 1 over n. So given a probability distribution for rolling a single line, and it's given at the bottom, we want to find the mean, which simply put, we are going to use this formula. And all you have to do, multiply the first column by the second column and add them up. So we're going to use this formula. The definition of this formula is very simple. Multiply all the x's by their corresponding p of x, or multiplying the x's by their corresponding probabilities. 1 times 1 over 6, 2 times 1 over 6, and all the way to the end. The last one is 6 times 1 over 6. And we add them up. It results in 21 over 6, or 7 halves, or 3.5. Let's find the variance and standard deviation. You can use any of those formulas. There are 2 ways to calculate them. So we pick one and we start. For example, sigma squared is x, the summation of x squared times p of x minus mu squared. So what does it mean? I want to make sure everybody can see that if we were looking at the table. X squared, that means if you look at the very first column, if you're looking at this one, squared, 1 squared becomes 1, 2 squared becomes 4, 3 squared is 9, 4 squared, and so on and so forth. You multiply it by p of x, and then you subtract the number that you found in part A squared, which is the mean squared, which is minus mu squared. This is what the formula does for us. So 1 squared times 1 over 6 plus 2 squared times 1 over 6 all the way to the end. We add them up, and then 3.5 squared gets subtracted from it. This is the variance, everybody. So sigma squared is 2.91667. Again, when you want to report that, depending on text you're working with, homework, and you name it, they may ask you for a specific number of decimals, or they may expect a specific number of decimals. So you want to follow that. I just wanted to show you, if we carry out more decimals, how it looks like, because it's important not to get to what's known as round-off error. So what is the standard deviation? All you have to do is take a root. So when you take the square root of 2.91667, that gives you the standard deviation. Let's see if we can see what it means. It's extremely important to understand the meaning of this calculation. Okay, so what? And that's the idea that is important when we do all of this calculation. If we were to collect data on rolling a single die many times, in other words, just keep on going. This is a general answer for mu for the population. And that means you have to, if you do it enough number of times, it gets closer and closer to the population parameter. Then you have the expected value, the mean, to be 3.5. In other words, if you add them up and divide by size, with a standard deviation of, let's say, 1.70, and if we do the rounding right here, remember, becomes 1.708. Pay attention to the way we do the rounding, because when you do the rounding, you want to be careful not to make a mistake. I was going to write with 3 decimals, and therefore I look at the 4th one and make a decision on the 3rd one. So that's the idea behind all of these calculations, the mean and standard deviation. So we are exploring this concept by looking at more examples. Here's the next one. We are given some data. As you can see, the probability distribution shows the number of trips of 5 days or more that American adults take per year. 5 days, 4 days, 7 days, whatever the case might be. And we want to find the mean. And again, let's understand, when you set up a table, you can set them up in this manner. And there are a couple of rows. Or you may set up with x and p of x as 2 columns. It doesn't matter. Now, let's make sure we understand the meaning of this table. This table tells us 6% take no trips of 5 days or more. I'm being lazy, I put 5D plus. That means 5 days or more. According to this table, 70% take 1 trip, that is 5 days or more. 20% take 2 trips of 5 days or more, so on and so forth. So this is the probability distribution, that the number of trips of 5 days or more. So now let's calculate mu, which is summation of x p of x. So that means multiply the top row by the bottom row. So 0 times 0.06, 1 times 0.7, all the way to the end. And so we add them up, and that gives us 1.23. and that is the expected value of number of trips. So what it really means is that according to this data, all American adults take an average of that many trips that are 5 days or more per year. So probability distribution of DRV, discrete random variable, and what it tells us. Here's the next example.
Recall, the table describes the probability distribution for the number of heads when 2 coins are tossed. A. Find the mean, variance, and standard deviation for the probability distribution described. B. Use these results in the range rule of thumb to determine whether 2 heads is a significantly high number of heads.
We are going to calculate mu, the expected value. When you're given tables, you can extend the table if we make up a new column called x p of x. And why are we interested in that? Because look at the formula for mu at the very bottom. It says mu is the summation of x p of x. In other words, the first column times the second column gives us this column we just made up, x p of x. So 0 times 0.25, 1 times 0.5, 2 times 0.25. And well, since they're all done at the same time, let me explain the next one also. We need to calculate the standard deviation, so we need to calculate the variance first. So if we use one of the formulas for the variances, for example, x minus mu quantity squared times p of x. First, you have to have the next column and the sum of that. When we do that, see what we get. 0 times 0.25 is 0, 1 times 0.5 is 0.5, 2 times 0.25 is 0.5, they add up to 1. So mu ends up being 1, and so the next column, x minus mu, so that means 0 minus 1, you're going to square that, becomes positive, times p of x, in the same column is 0.25, and that gives you 0.25. So you got to come up with this column and then add them up. The very last one that says the sum. So we multiply number 1, number 2, and we get number 3. 1 times 2 is number 3. We add them up, we get number 1. Now we use that to get to the last column. X minus mu, 0 minus 1, squared times p of x, which is 0.25. You do the same thing for the next one, you do the next thing, same thing for the next one, and you have all your answers. You add them up, and you're going to write them as follows. Mu ends up being 1. Sigma squared, we add them up to 0.5, this very last column. Now, sigma is the square root of 0.5, and it's like 0.707 or 0.71. So the calculation for this case, if we use a table, it makes it a lot easier. Let's go to part B. We want to use these results and the range rule of thumb to determine whether 2 heads is a significantly high number of heads. Remember, according to the range rule of thumb, we look at mu plus minus 2 sigma. If anything is beyond, it's unusual. The interpretation is that if we were to collect data on a large number of trials, that means you keep on doing that. With 2 coins tossed in each trial, we expect to get a mean of 1 head and standard deviation of 0.71. It really means that you have to do this many times. In other words, if you do this just 10 times or 20 times, it may not be enough that you get the expected value you want or the standard deviation. Just for the sake of argument, if you do that 10 times, it doesn't mean 5 times heads and 5 times tails. It may be like 7 and 3. When you do it 100 times, maybe 55 and 45. When you do it 1,000 times, then it gets closer and closer. That's the idea behind it. And so mu plus minus 2 sigma, that means 1 plus minus 2 times 0.7. According to the range rule of thumb, the numbers are between negative 0.4 to 2.4. So if we use this result, is this significantly high? The answer is no. Why is that?
It's because if the value is between the negative 0.4 and 2.4, then that means that it's not significant. If it wanted to be significantly high, it would have to be higher than 2.4.
Perfect. Look at the numbers. The upper number is 2.4, and since 2 is less than 2.4, we are in good shape. Let's go to the next example.
Lottery tickets cost $2, and out of 10,000 tickets printed, 1,000 have a price of $5, 100 have a price of $10, and 5 have a price of $1,000, and 1 has the price of $5,000. A. Let X represent the net gain and write the probability distribution for winning the lottery. B. Calculate the expected value and the standard deviation.
When we are given a situation like this, we should be able to come up with what's known as a probability distribution table. So what you need to do is to make up a table of 2 columns. In this case, it says let X represent the net gain, and it's important to know what's the meaning of a net gain. X represents the net gain. So if the lottery costs $2, that means the next net gain for everybody is -2 to begin with. Now, if I win the prize of $5, then my net gain is 5 minus 2. If I win $10, my net gain is 10 minus 2. So it's important to understand the concept of a net gain. The money that was paid for the ticket is gone. When we look at the tickets, we see that we have a total of 10,000, so they must add up to 10,000. So 1,000 have a price of 5, 100 have a price of 10. So far we have 1,000 tickets here. Then we have 100, let's do that. Then we have 5 that have a price of 1,000, and only one of them has a price of 5,000. So you add them up, and those are the winners, and you're going to subtract from the total of 10,000, and whatever is left is the rest of us that are playing and we are not winning. 1,000 are going to win $5, 100 are going to win $10, and so on. And look at the very last one, that's N, or the sample size, or 10,000 tickets. And how do we get to 8,894? You got to add 1,000, 100, 5, and 1, and that is the number that has to be subtracted from 10,000. That's 1106. And so with that being the case, what is the net gain? When you win $5, that means you won 5 minus 2. 10 means 10 minus 2, all the way to the last one, which means -2. So pay attention to this next column, especially this -2. So you have to put the number as a net gain. So the net gain for those 8,894 tickets or players is -2. Now the next column is very straightforward. Probability of winning. So how many are going to win $5? 1,000 people. So 1,000 divided by a total number of tickets. The next one, how many are going to win $10? Net gain of 8. 100 divided by 10,000. And so on and so forth. So we wrote the net gain probability distribution. Now the calculation, mu is summation of x p of x. So that means multiply the net gain column by p of x column and add them up. That would be x p of x. And then we can calculate the standard deviations, x times p of x. I want to go with that one here. And then I'm using this formula, x squared times p of x. So x p of x, that means 3 times 0.1. X squared p of x means 3 squared times 0.1. Next one, 8 and 0.01. So x p of x means 8 times 0.01. X squared p of x, as an example, let me just write the second one for you. So this one is 8 times 0.01, whereas here it's 8 squared times 0.01. So with that being the case, we add up this column, we get summation of x p of x, or mu. as summation of x p of x or negative 0.4. And what we have here is summation of x squared p of x. If you go to the top formula, you have to subtract mu squared from it and take a root to get to the standard deviation. So mu or summation of x p of x is negative 0.4. We use this formula and we take a root. I'm not calculating the variance, although you can, because you have to calculate the variance and then take a root. Either way is fine. So x squared p of x, we know the summation is 3001.1 minus mu, which is negative 0.4 squared. And when we go through the process, we end up with 54.78. What does it mean? And that's really important, the interpretation. Pay attention to mu. Mu is negative, and it is supposed to be negative for the players and positive for the house. So that would be the net gain on the average per player for the house, positive, and for us, negative. So the interpretation is, on average, a player, all players, everybody loses an average of 40 cents or $0.4 per ticket with a standard deviation of 54.78. It's important to understand, on the average, everybody loses. On the average, everybody loses, including all the winners. So I want you to see the concept. And that's how many things are calculated. Even car insurance or health insurance is calculated using this concept of expected. We could use a different method, and I'm going to mention it in this case, to calculate this, but it is not as detailed as this one for the expected value and the variance and standard deviation, but at the very least, the cost is $2. But what is the amount of prize? The amount of prize is 1,000 divided by 10,000 times 5 for $5 winners. That's why you multiply it by 5. For $10 winners, it's 100 divided by 10,000 times 10. $1,000 winners, 5 over 10,000, and there's only one that wins 5,000 wins big. And all of them, if you add them up in this fashion, if you will, minus 2 gives you the same mu, or the expected value, negative 0.4. So this would be another approach, but the previous one is more detailed.
$5 to place on a bet in a casino. Let's consider the following two bets. Roulette. Bet on the number 7 in roulette. The probability of losing is 38 over 30, 37 over 38. The probability of winning is 1 over 38. The net gain is $175. B, craps. Bet on the pass line in the dice game of craps. Probability of losing is 251 over 495. The probability of winning is 244 over 495. Net gain is $5. Which bet is better?
Which one has better expectation? E of x or mu? That's the idea behind the question. We are going to look at the two events, and we're going to put in the information that we have. So all we have to do, what is x, what is p of x? For the first one, losing is at -5. That means the $5 that we put in. However amount that we play, $10, whatever. And the probability is the next column, 37 over 38. We win 175, 1 out of 38. Now, for the next game, so for event A, if you will, roulette, and now event B, we do the same losing, -5, and has a different probability. Winning is also different, not just the probability. The amount of winning for roulette was 175, but for this one is only $5, but it does have a different probability. Now we are going to calculate mu, or the summation of x p of x. It means we have to multiply the two columns and add them up. The columns are x and p of x. Let's calculate their product and add them up. Okay, so we are interested in calculating mu equals summation of x p of x. So with that being the case, when we multiply -5 by 37/38, and then we multiply 175 by 1/38, and then we add them up, we get -0.26. We do the same thing for crabs, -5 times 251/495, plus 5 times 244 times 495. And they add up to -0.07. As you can see, both of them are negative. What does it mean? That means the roulette has a total of -0.26 for the players as the expected value, and it has a positive 0.26 value for the house. Craps has a mu, or the expected value, of -0.07 for the players and positive 0.07. And so here's the interpretation. When we bet $5, the expected value for the roulette is -26 cents. So every player on the average will lose 26 cents. And for craps, 7 cents. What does it mean? The craps game is better in a long run. And I can't emphasize this enough. Obviously, some people may go for higher risk, but that's how statistics work, the expected value. So for a long run, even though the roulette game provides an opportunity, a larger payoff when playing the game once. So in a long run, those are the gains. -26 cents for roulette, -7 cents for craps. By the way, the numbers that you see here, the probability that you see here, just for the sake of argument, if it changes for any reason, according to the type of roulette or craps is being played by a specific place, so be it. But this is the general concept as to how we evaluate things using statistics.
In a casino, the house wins on one of its games with a probability 50.6%. All bets are 1-to-1. Therefore, if you win, you gain the amount you bet. If you lose the amount you bet. If you play 200 games betting $1 each time, how much should you expect to win or lose?
We are going to go through the process and do the calculation for the event. And all we have to do, calculate mu by having two columns, x and p of x. That's what we are going to do. So here's the simple setup for the table. X, so the probability of the house wins, understand that means losing for a player. So the house winning, that means 50.6% there's a chance that we lose as players. If we play $1, so that means we lose that. Now, if this is the case, what is the probability of winning and the amount of winning? Well, we are playing with $1, let's say, or however amount. So that would be X, but what is the probability of winning? 1 minus 50.6%. That's how we arrive at that number, or 0.506. So the answer is 49.4% or 0.494. I put one of them as a percent on purpose because it's given as such, on purpose. Needless to say, really it makes no difference, and it's better to write both of them as percentage or decimal, but I did it on purpose. I want to keep it just the way it was given, and then 1 minus that. That's how we arrive at 0.494, because the sum of probabilities is always 1. All right, so we calculate mu, summation of x p of x. We multiply the first column by the second column. So -1 times 0.506 and +1 times 0.494, and we add them up. And this is the amount, the expected value, the average amount, the mean for winning in the case of one game. And that's for one game. What if we did 200 games? We multiplied by 200. So the expected value for 200 games would be the loss of 200 times the amount we found, which was negative 0.012. So again, for one game, the expected value would be negative 0.012. And for 200 games would be the same thing times 200, which becomes negative $2.4. This is the dollar amount. The next topic, in the case of a discrete probability distribution, deals with binomial probability distribution. We looked at probability distribution for a discrete random variable. We looked at definition of a random variable, the concept of a probability distribution that can be simply a table, a graph, or even a formula. And remember, quantitative data are in the form of discrete, that means countable, and continuous, that means they will take place over an interval. So if the moment we hear discrete or continuous, it refers to the fact that we are dealing with a numerical value. Now, for a probability distribution, we need three requirements. The random variable, RV, is numerical, and the values are associated with the corresponding probability. The sum of probability is always 1 or 100%, or it's extremely close to that. And the probability is always between 0 and 1. Then we looked at the formulas for variance, standard deviation, and mean. The parameters of a probability distribution are their mean and standard deviation. Mean, simply put, mu is E, or E of x is summation of x p of x. Sigma can be calculated as the square root of summation of x minus mu squared times p of x. And so now let's look at the new topic, binomial probability distribution. The binomial probability distribution, its mean and standard deviation, and we look at the interpretation of the probability values to determine whether events are significantly low or significantly high. So we are looking at binomial probability distribution.
Binomial experiment and PD properties. 1. N identical fixed number of trials, each repetition of the experiment. 2. Each has only 2 categories of outcomes. 3. Probability stays constant. 4. Independent trials. If a procedure satisfies these 4 requirements, the distribution of the random variable x is called a binomial probability distribution. It is the probability distribution for the number of successes in a sequence of Bernoulli trials.
First of all, PD short for probability distribution. We use BD short for binomial distribution. You are dealing with n identical repetition. For example, you toss a coin 5 times, 10 times, 20 times. There are 2 outcomes, heads, tails, yes, no, true, false. So that is really the main thing you want to pay attention when you're dealing with the binomial. And the probability from one stage to the next stage doesn't change. It is fixed, it is constant. And those are independent trials. If you look at rolling a single die, there are 6 outcomes. So it can't be a binomial distribution. However, if you're looking at the probability, you roll a die, the probability that the number is, let's say, odd or even. Now you have 2 outcomes. So it could be that although something has 6 outcomes, but you're really interested in making it into 2. So that is extremely important. If everything else works out, and most of the time they do, you want to pay attention whether this thing is working out or not. 2 outcomes. Now, as far as the notation is concerned, P is the probability of success. Q is 1 minus P, or the probability of failure. Make sure that the values of P and X refer to the same category called a success. X and P are consistent. X, a specific number of success in n trials. It's between 0 and n. Can it be 0? Yes. Can it be n? Yes, but it's nothing beyond it. P of X is the probability of getting exactly X successes among the n trials. For example, if you toss a coin, I don't know, 100 times, What is the probability of getting, let's say, heads 57 times, just as an example. The formula that is used is at top here. P of x is cnx p to the power of x q to the power of n minus x. I hope everybody remembers the shorthand notation. Cnx refers to n factorial over x factorial n minus x factorial. That is the combination.
The word success as used here is arbitrary and does not necessarily represent something good. Either of the two possible categories may be called a success S as long as its probability is identified as P.
It's important to understand success doesn't necessarily mean something positive. Success refers to what we are looking at. And whenever you're dealing with BD, and here's short for it, BD, short for binomial, you've got to be able to come up with N and P. Those are the parameters of binomial distribution.
Binomial coefficient, the number of outcomes containing exactly X successes. Each trial is known as a Bernoulli trial, named after Swiss mathematician Jacob Bernoulli. Notes, if the probability of X success in N trials is less than 0.05, it is considered unusual.
Again, the formula that I put up for you is being explained here. And as far as the terminology, Bernoulli trial, we simply call it a trial.
5% guideline for cumbersome calculations. When sampling without replacement and the sample size is no more than 5% of the size of the population, treat the selections as being independent, even though they are actually independent or dependent. Warning, if we toss a coin 1,000 times, P times H minus 501, or any specific number of heads is very small. However, we expect P at least 501 heads to be high.
Let me just make sure everybody is following what's happening here. We've already discussed this 5% cumbersome or difficult calculation, which simply put means there may be cases, remember, when we do it with replacement, it becomes independent, but without replacement, it is no longer an independent event, it becomes dependent. However, you can refer back to previous lectures that if the size of a sample is very small compared to the size of a population, then we can assume independence. The other thing is that when you do the binomial distribution and you're looking at a specific number of heads or tails, for example, if you toss a coin 1,000 times, what is the probability of tails happening 10 times or 50 times, or heads happening the same manner? It may not be a huge number, but happening at least 501 times, it should be very high, because we expect that to happen, sort of half and half when it comes to heads and tails. And now, what I want you to really pay attention to is the following. The probability of X is calculated as follows. Also, if we happen to look at the probability histogram for binomial distribution where P is 0.5, then we have a histogram which is symmetric. If it's less than 0.5, it ends up being right skewed, and you don't know that until you graph it and see it for a specific cases, and it's left skewed in the case of P larger than 0.5. What I want you to know is this formula and be comfortable with the concept. Capital P of X, this represents the probability of X successes, this one. But this P is the probability of success specifically for a specific case in general. So heads is always 50%. Again, for a fair coin. Tails, the same thing, 50%. That would be the case. Now, which one is probability of success? Well, depends on what we want. They happen to be the same. But even if it's not a fair coin, the probability of, let's say, heads is 60%, and therefore the probability of tails is 40%. Whatever that you're interested in getting, that would be referring to as the probability of success. The first one is the number of possible desired outcomes. That is a number, that's a combination. And then the probability of a desired outcome. The first one is how many ways it can happen. And the next one, the probability of a specific one. And we add to it the following important formulas. The mean or the expected value mu is equal to n times p. For a binomial distribution, mu equals np. And variance sigma squared is NPQ. Normally, we are not interested in that. We calculate standard deviation, which is the square root of that. Needless to say, you really don't need Q to calculate it. Understand that's why when we look at the binomial distribution, we need N and P only given to us. We can calculate the value of Q. So that's why Q is not a parameter. It's something that we can easily calculate. It's important to distinguish between the two concepts. What is a parameter and what is not? Q we can calculate as long as we have P. These are the formulas that we are going to use in this section. Let's look at a couple of examples.
When an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. A, does this procedure result in a binomial distribution? B, if this procedure does result in a binomial distribution, identify the values of N, X, P, and Q.
It's important to understand that it is selected with replacement and therefore they are independent. But even if it's not, if we are looking at the number, it's huge for the number of users. And so they can be treated as independent. That's the idea that was discussed previously. Now, basically, the most important question you want to ask yourself, how many outcomes? That's why if you look at the top right in blue, it is giving us the requirements for a BD binomial distribution. The most important thing would be to realize there are 2 categories. So there are 5 trials, N equals 5. There are 2 categories. The selected person knows what Twitter is or doesn't. The probability for each randomly selected adult, okay, in this case, we chose X equal 3. The P is 0.85, Q is 0.15. They are independent, different adults. Verify that. I expect you to do the following. The moment you read that question, you should recognize, here's the given, because this is a word problem. So the given that you should recognize what you're dealing is, it's BD, short for binomial distribution. You should recognize it is, there are 2 outcomes. And if you are claiming this is binomial distribution, you should be able to come up with N quickly, 5 randomly selected adults. It doesn't matter, 3 of 5 or 2 of 5 or all of 5 or 1 of 5 or none of 5. How many do we have? N equals 5. The probability of success in this case refers to knowing Twitter. So that would be 0.85. I expect you to write this at the very least for your own to understand 2 things. Number 1, you're dealing with the binomial distribution. And number 2, you need to know 2 things, the parameters, to know just about everything there is to know about binomial distribution. That's N and P. Now, you don't need to know, you don't need to be given Q. Q is 1 minus P. I can calculate. And then you look at the question, and now for X equals 3, you are going to do the calculation class. But again, I can't emphasize this enough. BD stands for binomial distribution. N is 5, P is 0.85. This is it, I'm done. This is my binomial distribution. I'm telling my reader, this is the distribution I have to deal with. Now to do the calculation, I need to know what's Q. I'm going to write it as 1 minus P and get there, and whatever X may be for the question. So N is 5, P is 0.85. Those are the information we need to begin with. Now X is 3, and Q is 1 minus P, or 0.15. These 2, again, this can be calculated, and X is not a parameter. So having said that, let's calculate P of 3. Look at the very top formula, P of X. So I want you to pay attention to this one, the very top formula. We're going to replace the N with 5, and we're going to replace the X with 3. If we were to write the general form before even we move on to 3 specifically, we could write it as follows. Now, let me write it here. So we would write P of X is N factorial over 5 minus x factorial times x factorial p 0.85 to the power of x, q 0.15 to the power of n 5 minus x. So take a look at the formula. Now, why am I writing this formula? All you have to do, replace the x for whatever the case. There may be 4 or 5 different parts of the question you want to answer. You replace the x with the number that you want. For example, if we were to write the probability distribution for this guy, we would replace the x with 0, then 1, 2, 3, 4, 5, and calculate all 5.
Can we just use the combination if we don't want to use the factorial?
Sure, you can use a combination, but it is a combination. It is a combination of n, choose x. But I'm explaining the general formula for the binomial distribution for this specific case is what you see, and then replace the x accordingly, because you may have different parts where it's asking you, for example, when x is 3 or x is less than or equal to 2 or x is larger than or equal to 4. Do you follow what I'm saying? So this is a general case. Now, specifically for x equals 3, we plug in. And you're right, the first portion is just a simple combination. You do the math, you put it into a calculator, it does the job for you. I'm assuming nobody has any problem with the calculation of that. And it gives us the answer, which is 0.1382. So the probability that exactly 3 out of 5 randomly selected adults know what Twitter is about 0.1382. If we said at least 3 know, then the number will be much larger. Now, it is important that you understand the concepts, how it's calculated. I want to show you quickly how to use your calculator. So you can use a binomial distribution as follows. Second, vars or variables, then binomial PDF, you enter npx, you click enter. If you enter n and p only, it gives you all probabilities from 0 to n. If you're using binomial CDF, gives some of the probabilities from 0 to x. So take a look at this one. If you put the binomial PDF 5, that's your n. 0.85, that's your p. 3, that's your x. It gives you the answer. So it can be calculated that way, but it is important that you know the concept. Depending on the TI that you have, 83 or 84 may be slightly different. This is from TI 84. For binomial PDF, you put the number of trials, you put the P, you put the X value, and you press at the end enter, and that will give you the results. Here's the next example.
Assume 1 out of 5 people has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 have visited a doctor last month. Find the probability that at most 2 have visited a doctor last month. Find the probability that at least 3 have visited a doctor last month.
I will look at other examples similar to this. I have left parts B and C for you to do it. After we do more examples, you should have no problem with that. You're more than welcome to ask me if you have a question. It's very straightforward. Now, as far as this question is concerned, we either have visited the doctor or not. So again, it's important to recognize this is a binomial distribution. There are 2 outcomes, and we're dealing with different people, independent, and so on and so forth. The main thing is to recognize there are 2 outcomes. And if this is the case, then you must come up with n. 10 is the value of n. Remember, probability of success refers to what we are interested in calculating. It doesn't have to mean something positive. Okay, visiting a doctor, for example. You're dealing with a binomial distribution with n equals 10 and p equals 1/5. In part A, we want x to be 3. Now, we need to calculate q. Q by definition is 1 minus p, so that's an easy calculation. So you're dealing with a binomial distribution, n is 10, p is 1/5. Please understand, this is the part we need to know, and then we add other parts depending on the question. So for binomial distribution, you need the n, you need the p. I can't emphasize this enough. So in part A, x is given as 3, and we can calculate the q as 1 minus p, which is 4/5. And this is what I was explaining in the previous example. You write the formula in general. It's important to understand what happens. So for part A, or even any other part, you just write the P of x as follows. We keep it as x, 10 factorial, over x factorial times 10 minus x factorial, P, which is 1/5 to the power of x, times Q, which is 4/5 to the power of 10 minus x. So all you have to do for part A, replace the x with number 3. If we replace the x with number 3, or you can use a calculator. Again, I want you to see the concept. It's important that be able to write the steps, and then at some point you use a calculator. Now you replace the x with 3, and it ends up being 0.20133. So the probability that exactly 3 have visited the doctor last month, according to this case, is about 20%, 0.20133. For part B, it says find the probability that at most 2. Let's write it. P of at most 2 means what? X is less than or equal to 2. At most. So I want you to understand the concept of at most. If it's at most 2, then you need to calculate probability of 0 plus probability of 1 plus probability of 2 by putting it in this formula, letting x be 0 and then 1 and 2 and add them up. That would be part B. So everybody can finish that. How about part C? Let's write it down. Probability of at least 3. That means probability of x larger than or equal to 3. We simply put, if we were to calculate it, would be P of 3 and then 4 all the way to n. You have to go all the way to n. However, probability of x larger than 3 is the same as 1 minus probability of x less than or equal to 2. And you've already done part B. So you really have to do subtraction. In other words, 1 minus part B. So all you have to do, calculate part B. And C is 1 minus that. By definition of at least and at most, you should be able to calculate this. So let's go to the next example.
A survey found that 30% of teenage consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. Find the probability that at most 2 of them will have part-time jobs.
It's a BD, binomial distribution. How do we know that? We either have a part-time job or we don't. Yes or no. So, and of course, independency and consistency, all of the above. But the main thing is to understand n and 5. So as we look at this portion, we should recognize we are dealing with BD. Therefore, n is 5, p is 30% or 0.3. Now we follow the rest. We can write the general format, replace the n with 5, p with 0.3, calculate q as 1 minus 0.3 or 0.7. And so if we want at least 3, let's see what happens. Probability of at least 3, that means probability of x larger than or equal to 3. Therefore, you need to calculate x equals 3, 4, all the way to n. N happened to be fairly small, it's 5, so it's really not that big of a deal. In other words, you have to use this formula first. P of x is n factorial over x factorial times n 5 minus x factorial times p 0.3 to the power of x times q. Q is 1 minus 0.3. Q is 1 minus 0.3, which is 0.7 to the power of n 5 minus x. Now in this formula, you replace the x with numbers 3, 4, 5, and add them up. So this is for number 3, We have the general formula in blue. We plug in number 3. We come up with the answer. We plug in number 4. We come up with an answer. We plug in number 5. Needless to say, 0.7 to the power of 0 is 1. And now you have to add all those numbers. So add them up. And that's your answer for part A. So that's for at least 3. The next part is asking for at most 2. And at most 2, that means probability of x is less than or equal to 2. And you have to calculate the probability of x equals 0, x equals 1, x equals 2, and add them up. However, because at least 3 was already calculated, and we realize probability of x less than or equal to 2 is 1 minus probability of x larger than or equal to 3, we can use that one. So when we use that one, it's just a simple calculation, 1 minus the part A, and that's the answer. It can be done by technology, but you really need to understand the concept right, some parts, and then if you need to add technology to speed up the process. As an example, if you go to the top box, TI calculator binomial distribution, number 7 says if using binomial CDF gives sum of the probabilities from 0 to x. Because we want x less than or equal to 2, we can write n, p, and x in that order, and it gives us an answer. Now, if you were to use the technology, in essence, you really have to use part B first, and then A would be 1 minus B. If you want to use the binomial CDF, just the way it is, for part A, it's 1 minus part B, because the way binomial CDF works, after n and p, you have to use x. What does that mean? It calculates the sum of all the probabilities from 2. But from what? From the beginning, from 0 to x. So if you want at most any number, it will do the job for you. Just put that number. But if you want at least, it doesn't do it. So you have to look at the complementary event to be able to handle it properly. If you're using the technology for part A, part B must be calculated first and understand we arrive at that, and then A is 1 minus that according to complementary events. Here's the next one.
It is reported that 2% of all American births result in twins. If a random sample of 8,000 births is taken, find the mean, variance, and standard deviation of the number of births that would result in twins. Use the range rule of thumb to find the values separating the numbers of twins that are significantly low or significantly high. And is the result of 200 twins and 8,000 births significantly high?
Before we do this question, it is the recognition of what type of probability distribution we are dealing with. It is reported that 2% of all American births result in twins. So that means either there is a twin or not, yes or no. There are precisely 2 outcomes. Okay, that's important to understand. So it is important to recognize it is a binomial distribution and why. And of course, we are assuming all independency and so forth. It's easy to assume independency. There are 2 outcomes. So you are going to write BD. And if you are claiming it's BD, you have to come up with N and P. So N is 8,000 and P is 0.02. And remember, it's considered the probability of success, whatever event we are interested in. And so we can calculate the mean, and they are not asking for anything else. So all we have to do, look up the formulas above and see what's mu and what's sigma. Mu is N times P. Sigma, it's N times P times Q, and take a root. Q is 1 minus 0.02 or 0.98. So Q is 1 minus 0.02. So mu is N times P. You multiply the 2 numbers, you come up with the answer. Sigma squared is the product of 3 pieces, N, P, and Q. And again, Q is 1 minus P. You come up with the answer. And now you need to take a root. Sigma is the root of that number, is 12.522. So we got the mean, we got the variance, and we got the standard deviation. We got all of those. So that's part A, very straightforward. Mu equals NP, sigma equals square root of NPQ. Now the range rule of thumb simply puts as mu plus minus 2 sigma. So 160 plus minus 2 times 12.522. And so if we subtract 2 times sigma, we get 134.956. And if we add 2 times sigma, we get 185.044. That means anything less than 134.956 is unusual. Anything larger than 185.044 is unusual. So now that we have that, what about 200? Is it significantly high? According to part B, yes, it is, because it's larger than 185.044. That means 186 is unusual. Less than 134.956, that means 134 is unusual, okay? You can keep it with the decimals just to give, although the answer should be discrete, but I want you to understand. Even if it was, let's say, 134.1, that means 134 is unusual, okay? Although it's very close. And that's the idea behind this process. Let's look at one more example.
McDonald's has a 95% recognition rate. A special focus group consists of 12 randomly selected adults. A. Find the mean, variance, and standard deviation. B. Use the range rule of thumb to find the minimum and maximum usual number of people who would recognize McDonald's. C. Is the result of 12 people in a group of 12 recognizing the brand name of McDonald's unusual?
We are dealing with a binomial distribution. We have to be able to come up with N and P. In this case, you are dealing with a binomial distribution. N is 12, P is 0.95. Again, mu is N times a P, 12 times 0.95. And to get the variance, sigma squared is N times P times Q. Q is 1 minus P, or 1 minus 0.95, or 5%, or 0.05. And so we have mu, we have sigma squared. To get to sigma, we take a root, and we end up with 0.75498. Now, the next thing is finding, using the range rule of thumb, and finding where we stand as far as our unusual. Mu plus minus 2 sigma needs to be calculated. So that means 11.4 plus minus 2 times 0.754983, and we end up with 9.89 and 12.91. Meaning, in a case like this, if less than 9.89 people recognize the name, that's unusual. For example, if only 9. And larger than 12.91, for example, 13. Therefore, the answer to part C is this is not unusual.